Hello everyone and welcome back to the second part of the first video lecture. In this video I will explain to you the basic principles of radiodiagnostics, the basics behind an X-ray machine, how an image is created and some basic image properties. Like you can read here, the definition of radiology is the medical discipline that uses medical imaging to diagnose and treat diseases within the body of animals, including humans. Obviously, radiology is able to diagnose certain pathologies, but we also can use it to treat patients. Not the X-rays itself, because that would look like radiotherapy, but with the help of radiological techniques, a physician is able to perform interventions. You can think about implementing pacemakers or performing biopsies, for example. When it comes to radiology, there's a great variety of techniques. First, there is a bucky, which is the X-ray room where static X-rays are made. Second, we've got a CT scanner, which uses X-rays to make computer rendered images of the body. Third, there's fluoroscopy, where X-rays are used to make live video-like images. Those are often used in interventions such as surgeries. But radiodiagnostics is also ultrasound and MRI, which don't use X-rays. All these techniques are found in modern radiological departments. Okay, this is an example of a bucky room. This photo is taken in the practical rooms at Fontys Paramedische Hogeschool. In these rooms, the practicals are given, and also you will practice here independently. Instructions on how to use this device will be practical number 1. In blue, you can see the X-ray tube, the handle and its block below. Behind the handle, that is the diaphragm, which is used to make the field smaller or wider. Out of the tube comes the beam or bundle of X-rays, which passes through the patient and falls on the detector, which is depicted here. This detector is used to capture these X-rays and convert them into a digital signal. From this detector, the digital signal is transmitted to the computer, which shows this signal as an image on the monitor or viewing station. How this works, we will come back to you later this year. Apart from this, a bucky room also contains a generator which produces the high voltages that is needed to produce X-rays. This generator is able to produce hundreds of thousands of volts. So you might not want to spill your cup of coffee over it, because that might turn ugly. Also, you see a sink, which allows for hygiene, and obviously a table on which a patient can lie on. This table can go up and down with the pedals you see below, and also another pedal makes it for the table to almost hover, which makes for easier patient positioning. When we look at X-rays, we are talking about a form of electromagnetic radiation with high penetrating properties. For the people who had physics in high school, you might remember the electromagnetic spectrum, which contains microwaves, which contains visible light, ultraviolet light, but also the real powerful waves like X-rays and megavolt rays. In imaging, we use the penetrating power of X-rays and its partial absorption inside of the body to generate images. Well, these rays, X-rays, can also be scattered, but let's first look into the top two. Well, like I said, an X-ray bundle or beam passes through the body where some X-rays are absorbed and some are not. Bone absorbs a lot of X-rays. Soft tissue absorbs less, air absorbs very little. Intensities change in the outgoing beam, which are detected on the, by the detector. Okay, so like I said, bone absorbs a lot of X-rays. So bone is depicted white. Soft tissue, like the heart, are depicted gray. Air is depicted black. The image is divided into pixels, and each pixel gets its own shade of gray. In radiology, but also images in general, we can define multiple properties to assess or evaluate an image. One of them is brightness. It refers to the overall lightness or darkness in an image. Here you are given two examples where there's either too much or too little overall lightness or brightness. It results in a suboptimal contrast because either the extreme white or the extreme dark colors are not used. So what is contrast? As you can see on this slide, we define contrast as the difference in grayscale in the image, which is caused by the difference in outgoing intensities on the detector. The better you can distinguish different kinds of tissue with different attenuation properties, the higher the contrast. So, bone is pictured white. Remember, soft tissue is gray, air is pictured black. In this slide here, you are shown two examples of either too low contrast or too much. In the left picture, you hardly see the difference between bone and air, and in the right example, this difference is way too high, too great. Too high contrast means that you can't see the subtle difference in attenuation inside bone, which you can see in the middle image, which is an optimal contrast. All right, so the image therefore uses the fact that radiations are partially absorbed. We make grateful use of this, but there's also a downside, because the absorbed radiation can also cause for biological damage inside of the body. Therefore, the ALARA principle is our main starting point when it comes to administering radiation to our patients. Really see this as one of the golden rules of radiology. ALARA, as low as reasonably achievable. Ways how you can account for the ALARA principle in radiology are, for example, assess whether a study which is to be made by because a physician asks you to can also be done in different ways. Think about ultrasound or MRI. You can keep the field borders as small as possible, which makes for less radiation, and you can keep the dose as low as possible. Like I said before, X-rays can also be scattered. X-rays pass partially through the body and are absorbed to a large extent by the body, which again makes for the contrast. But in addition, X-rays are also partially scattered throughout the body due to the collision of X-rays with the atoms inside of your body. Those scattered X-rays are scattered and emitted in all directions, both outside and inside the body. But what does that mean for the patient and for the radiographer and the X-ray itself? Well, the larger the volume that is photographed, the more scattering radiation inside of the patient. Thus, the higher the radiation load dose for the patient. Radiation outside the patient can reach someone standing next to the patient, for example, the radiographer. That's why it's very important that everyone except for the patient is behind the safety glass while the X-ray is taken. Radiation falling on the detector disturbs the X-ray and thus has a negative effect on the contrast image. Due to the facts I just named, we want as little scattering radiation as possible. We can achieve this by keeping the X-ray field on the patient as small as possible, and also other aspects which we will discuss later on this year. If you would like to read more about this subject, the book of Bouchon has a really good physics chapters inside of it. For the Dutch students, also the book of Hansen, Radiology, Techniques and Research, is a real good literature to take into account for this subject. Like I said before, obviously no live questions in video lectures. Save these for the consultation moments or even the practicals. Thank you for listening. Good luck and bye-bye.